Okay.
We're very happy to have Kifung from Chinese University of Hong Kong tell us about 3D mirror symmetry is mirror symmetry.
Okay, thank you very much for the invitation and the introduction. Okay, so I will begin with a comparison between 2D mirror symmetry and 3D mirror symmetry. Maybe I use a bigger block. So 2D mirror symmetry. So we have the spaces Y and Y chat. They will be Calabi-Yau manifolds, or in general, Y may be some kähler with some anti-kähler divisor, and then Y chat will be some Ginsburg model. I mean, yeah. Or more general. Okay. And we'll talk about the branes. So in 2D, there are A side and B side. So our brane in the A side will be a Lagrangian, a real Lagrangian, together with a fat local system, fat U1 local system. And the branes in the B side will be a compact submanifold. Together with some holomorphic vector bundle. Okay. And we also consider the moduli or the deformation of the spaces. So there are symplectic moduli or the complex moduli. So in 2D mirror symmetry, so Y and Y chat are said to be the 2D mirror, and the SYC conjecture says that there will be an SYC transform. Okay. And in the branes level, there will be some Fourier type transform. And the corresponding, sorry, yeah, the Fourier transform. I mean, when you have a Lagrangian brane, you can take the dual, fibrilize take the dual. And between the compact and symplectic, this is called the mirror map. Okay. Okay. This is a 2D picture. Okay. And let me draw a similar 3D picture. Okay. So 3D mirror symmetry. So we also have a spaces. So X and X rig. Okay. And they will be compact symplectic. And there are 3D branes. Yeah, I will talk with more details later, but now a 3D brane is just a compact Lagrangian. Together with a family of kähler manifold. The same for the other side. Compact Lagrangian together with kähler manifold. Okay. And the analog of the moduli or deformation will be the kähler parameters and equivariant parameters. Kähler parameters and equivariant parameters. Yeah. And our work is trying to understand 3D mirror symmetry in the framework that is somehow similar to the 2D mirror symmetry. Okay. So for the 3D ring transform, we expect that will be an SYC type transform, which will be the main object of today's talk. Yeah. And let me call the Kähler the exchange of Kähler parameter and equivariant parameter to be the 3D mirror map. So one of the idea is that the 3D mirror map is induced from the 2D mirror map. Yeah, that partly explains the title of my talk. So the 3D mirror map is related to the 2D mirror map. And for the space level, we also expect that the 3D mirror can be grouped. There are some kinds of group. Yeah, there is some process to group the 3D mirror by Lagrangian correspondence. I will describe more details later. Okay. Any questions so far? Yeah, I will explain all. Okay.
Is it the organized deformation between of Y or the ring?
Of Y. Okay. Okay, so let me write down a proposal explicitly. So yeah. So I will first write down the proposal and then give some example and then describe everything in more details. Okay, so first, so X and X rig are 3D mirror. Okay, so there exists an SYC type transform. So from branes of X to branes of the 3D mirror. This is the 3D branes in X. And for the second, the second part of the proposal is that the exchange of complex and symplectic structure in 2D will induce the exchange of Kähler and covariant parameter in 3D. Exchange of symplectic and complex structure in 2D induce the exchange of Kähler and equivariant. In 3D. Okay. And the third part is that the Lagrangian correspondence is 3D mirror to Lagrangian correspondence. So yeah, so in particular, if your X is the union or some space which you have a better knowledge of their 3D mirror, then its 3D mirror, yeah, can be obtained from gluing, yeah, the 3D mirror. Of course, the gluing can be very complicated, yeah. So in this talk, I will discuss some example and to tell you I mean by the gluing.
Can you explain all the 1, 2, 3? What do you mean, for example, by S1? You'll tell us.
Yeah, I will tell. I will first give some easy examples so that you have some example in mind.
Now, get colored out. So do you want to write here or?
Or maybe I just erase the other. You mean I should use this box? Okay. Yeah, before telling you much detail, I will just give you some examples first. So, okay. So I will tell you, so the abelian 3D mirror symmetry. Okay. So suppose you have exact sequence of complex tori. So yeah, C star K to C star N to C star N minus K. And the dual sequence. Okay. And an example of the 3D mirror pair will be an X is potential bundle of Cn, symplectic quotient by that C star K. And its 3D mirror will be the potential bundle of Cn, quotient by that C star N minus K. Yeah. Okay. So let me draw a table to tell you what will be the result of the SYC type triform. Okay. And so 3D. Okay. So for example, when X is potential bundle of polynomial C star, the 3D mirror will be T star C star. So bring in X will be some Kähler manifold Y together with a C star action. Yeah. I will tell you the precise meaning of 3D plane later, but yeah. So now just bring is just a C star action acting on some Kähler manifold Y, and bring in the 3D mirror will be some space Y check together with a map. Okay, and the 2D interpretation will be the element conjecture, which says that when you have a C star action on one side, then the 2D mirror will have a holomorphic map to C star. And the other example is C over X is T star C quotient C star. The 3D mirror T star C. Now bring in X will be a Y together with a divisor. Bring in X weak will be Y check together with some function. And the 2D interpretation will be the mirror symmetry for log Calabi-Yau, or mirror symmetry for Kähler manifold with a divisor. Okay. And one more example will be T star C2 1 minus 1. I mean, when C star acting on C2 with the action, it has weights equal to 1 and minus 1. The 3D mirror is also C2 quotient C star, but the weight is 1, 1. Okay. You can think it as T star P1. Okay. So a 3D ring will be a two-ring degeneration. A 3D ring in the mirror will be some mapping to P1. And this is related to the DXT conjecture. Yeah.
I think related to 2D version, what do you mean? So
what do I mean by relation?
The equivalents on the left side of the right part of the board are in 3D. Those are 3D.
These two are 3D.
Yeah.
And this will be a 3D rings.
Yeah.
Yeah.
Yeah. 3D coil on it.
And Y and Y chair will be 2D mirror.
Yeah.
Yeah. What I'm saying is that when Y has a structure as a 3D ring in X, then Y chair will have a structure of 3D ring in X rig.
So what?
As a structure, as a 3D rings in X rig.
And by your column, your 2D column, we mean something like
how to interpret this result using 2D mirror symmetry.
that the boundary theory gives you already know.
Yeah, exactly. So for this kind of transform, we already have a name for the 2D.
For the 2D,
yeah.
The boundary.
Yes, exactly. Thank you for asking. Okay. Yeah, I will explain some of these later. But let me give you an example to explain the second point.
There's some systematic way of dealing with the table, and that
Yes, that's.
People did not know about.
You can say so, but essentially all the. Yeah, there is. But essentially everything just built on the first and the second example, essentially. Yeah, for abelian theory. Yeah.
Are you going to have some systematic procedure for non-abelian theory?
I mean, for non-abelian theory, we will first do the abelian theory and then try to show that the transform in abelian will lead to the non-abelian transform.
But you believe that there are some general statements that go.
Yeah, I believe so.
And which way does it go? You say 3D mirror symmetry. I mean, am I discovering new examples of 2D mirror symmetry, or knowing those?
You will discuss. Yeah, you will discovering some new phenomena in 2D mirror symmetry. Yeah. Okay. Yeah, although the abelian part may not be that interesting. Okay. So for point 2, let's consider the case where X is T star P1 and its mirror is also T star P1. Okay. And this is the Hallway picture for T star P1. Okay. Okay. So in our transform, so this zero section will be mirrored. The 3D mirror brane for this zero section will be some Lagrangian F here. So the T star P1, bring a P1, and it will be 3D mirror to C star P1 with some Lagrangian F. Yeah, and the point is that this. Okay, so this Lagrangian has some symplectic form. So the P1 has some symplectic form. And the F, the F will intersect this cotangent fiber at one single point. And this point, this intersection will depend on the symplectic form. Depends on the omega on P1.
Wait, there's some complex one that's inherited from star P1.
Yeah, I mean, if you have a symmetric form on T star P1, you can restrict it to the zero section and then use it to deform the sympathetic structure of the brain. And in the mirror side, you will deform the location of the mirror brain.
Deforming the location of the mirror. This can correspond to a complex deformation.
Yes, you should think it.
Generate object, then compare the deformation of the higher structure on the X. Right?
I mean, you should think it as a family over the CO fiber, over the cotangent fiber. And then if you deform it, then the family will change. Yeah. It does not deform the complex structure of F, but deform the complex structure of the family. Yeah. Yeah, because the fiber are changing. Okay. Oh, sorry. Okay, for part 3, let me. Okay, sure.
About mirror symmetry for P1, right?
I mean, yeah, this is P1. Okay, and this is C2 quotient by C star. I mean, yeah, maybe I.
Mirror P1, not that given one, right?
Yeah. I mean this location. So this is P. This P is just the C star 2, which is the 2D mirror for P1 deleting the C star. There's a mirror for P1 deleting the divisors, and it has a map to C2, which is Z and 1 minus Z. Yeah. And this is the cotangent fiber. So if you want the omega to appear, so you better change the other coordinate to Q over Z. That's why when you're changing the symmetric form, the Q will change. And the precise location for P is changing. Any other questions? Okay. Okay, so let me give you an example. So for T star P1, it can be understood as the union of two different T star C with their intersection being T star C star. Okay. But for the mirror side, for the 3D mirror side, there are no such maps. There are only Lagrange correspondence. A better way is to look at the CO section. Look at the CO section. So it's P1. Maybe I'm P1. If you look at the zero section, there is a push-out diagram. And on the other side, the 3D mirror for this 4 will be T star C2 quotient C star, T star C quotient C star, T star C quotient C star, and T star point quotient C star. So once again, if you look at the zero section, you will have C quotient C star, C2 quotient C star, C quotient C star, and also point quotient C star. But all the error are reversed. And this will be a Hilbert diagram.
But you can use it as this mirror.
Yeah, this is one of the example. Okay. So there is another example that I will talk about later, that you can use similar idea to obtain the Telemann schooling. You mean taking this? Yeah, it may probably a fiber here. Yeah, just.
And so, I still don't quite understand the thing about P. Are you claiming that given T star P1, the P is fixed? Because the electric structure of P1 is part of the, I mean, it's a F5 parameter of the, or like a covariant parameter, which depending on.
I mean, by giving a P1, you also give me the symmetric form. Symmetric form is part of the structure.
Is it inherited from the bulk or not? Is in other words,
it does not necessarily.
With a fixed position, with a fixed P, or do I get to duality?
It depends on whether you vary the symmetric form. Yeah, it depends on your perspective. Okay.
So it's not fixed by the bulk. I mean, you think you want to think of.
Yeah.
Being able to vary independently.
Yeah, yes. Yeah, and the variation correspond to the equivalent parameter on the mirror side or the Kähler parameter before the mirror. Yeah. And the other example is you can obtain Telemann schooling, which you can obtain the Coulomb branch for a gauge theory with methods by going to pure gauge theory Coulomb branch. Okay.
Changes Kähler and covariant parameters. Can I think of them as fixed? I give it to you and then I get X and extra.
Yeah, you can think it as fixed.
Okay, so I fix those.
You fix those, but you do not fix the symmetric form of the branes. Even you fix the symmetric form of T star P1, if you have two different symmetric form for the P1, then you have two different things.
Part of the data of the brain will be a choice of symplectic form on the brain, which I
Yeah.
down.
Sure, sure.
That's obvious.
No.
Okay, fine, good. But I see that your picture says that it has to.
Okay.
Right,
Yeah. Okay. Okay, any questions? Otherwise, I will just explain with more details.
Sorry, what is number 3? Isn't it the same example? I'm a little confused. Why are you distinguishing this example at that time?
In 3, I'm explaining that Lagrangians are 3D mirror to Lagrangians. I mean, Lagrangian correspondence are 3D mirror to Lagrangian correspondence. So for T star P1, it is a union of two different T star C and.
You asked about Lagrangian correspondences in 2D. You want to tell me that there is, I should also think about Lagrangian correspondences
In 3D. Yes.
Okay, and what do you mean by Lagrangian correspondence? But I mean, you first have, it's a correspondence between what and what?
It corresponds between two compact symplectic space. Yeah, just for this example, so just the inclusion is a compact Lagrangian correspondence.
Okay.
Yes. So I'm saying that is, before the mirror you have map, you have morphisms, but after the mirror you do not have morphisms. But you only have morphism in the in the zero section level, and this will give you the Lagrangian correspondence. Mm-hmm. Yeah. Yeah.
I think he's saying like he's decomposed it into pieces, and each of the pieces are themselves like big branches and Coulomb branches of some theory.
Sure.
They want to say, well, if you have like the big branch and Coulomb branch, some theory included into the other one, that's the map between them. The graph of that, the big hallmark of the branch is the top.
Okay.
So then it says like, you know, by viewing those interfaces, you get these kind of diagrams.
But this has nothing to do with 3D mirror symmetry. I could have, in fact, it's a
No, but it's like
example.
the things he has on the zero section level are like 3D mirrors. Because you would say like C star is like half the Coulomb branch of pure gauge theory, which is 0.1 C star. C is half the Coulomb branch of D is half the Coulomb branch of dual point hyper, which is C not C star.
Yeah, we will see this picture is compatible with the SYC transform. I mean, you can see the push out and pull back.
SYC transforming T star P1, or I'm SYC transforming IC6. So you want to think of S both, because the brains are inherited from.
Yeah. Yes, exactly.
Inherited.
Yeah. Okay. So for this example, the P1 is this guy. And this is C. This is another C. Okay, so for this example, just look at the zero section, P1 contains 2C, nothing to do with these two fibers. Okay, yeah. Okay.
You assume it not sound good, and some people here do. In particular, so
yeah, I will explain later. Yeah, okay. Yeah, because that involves more notations. Who's that? Thanks. Thank you. Okay, let me explain what I mean by SYC transform. Or SYZ. Okay. So, sure.
So, pick any one of these values. What is the corresponding Lagrangian correspondence like? The first one.
The first one. Yeah, I mean, so you have a map from T star C to T star P1, right? Okay, and this map is F, and the graph of map will be a subset of T star C times T star P1. If you change the first symplectic form to its minus, then this will be a Lagrangian, and that's the Lagrangian correspondence.
Okay, completely. Which one?
Yeah, like,
It's a graph.
like just take the point in T star C and the point that is the same T star P1.
Yeah. Yeah. Basically the diagonal. Okay. Okay.
But again, it must be so. What is the claim? So suppose I give you a 3D mirror pair.
Yeah.
The statement is then what? What statement about Lagrangian correspondence can I make?
Lagrangian correspondence.
That's all what you do. So a hypertoric manifold is Flavian, so I can always talk. It's a particularly.
But if you take the XYZ transform of the ring, get another ring in the product of the mirror, you can use that.
Where do we use that?
I mean, when you have a Lagrangian correspondence, you can have a transform from rings on T star C to T star P1. And what I'm claiming is that this transform is compatible with that Lagrangian correspondence. Yeah, but I need to define the SYC first before telling you why this is true. Okay. So let's say Y is a kähler and D is an anti-canonical divisor. Okay. So Y is kähler. So what I mean by SYC mirror is that I will take Y check to be the moduli space of L and E, such that L is a special Lagrangian and then E over L is some U1 local system. That's what I mean by the SYC transform. Okay. Okay. So if there is a torus action acting on Y, then we will preserving all the structure, preserving omega Y and also JY. Then we will also assume that L is T invariant. Yeah, only for the abelian group. Yeah, that's what I mean by the SYC transform.
SYC, you gotta slow down because SYC transform depends on the choice of SYC vibration.
Yeah.
So the statement is true with some choice of SYC vibration. It cannot be a general thing because it depends. So which SYC vibration am I choosing to get this thing?
I'm not choosing a SYC vibration, but
The SYC transform. So
yeah, I mean I define it in this way. Just any special Lagrangian. Or in other way, you can choose any special Lagrangian. I see. The special Lagrangian. So that's anti-chaotic divisor. So it means that there is some meromorphic volume form of Y such that B plus the divisor is equal to 0. And the special condition means that the real part of it restricted to L is 0. Yeah, but it's not so important for this talk.
you think
Yeah.
Can somebody help me out with
I mean, maybe you can just taking anyone. Just choose one. Choose one. If you have an action, then you choose.
Okay, great. So, maybe you can give us an example for. So, great. What's my SYC? Take an example of there. What's my SYC base?
Yeah, for that example, like for example, P1.
How do I see the framework?
You just choose this vibration for P1.
Yeah, so now I have a problem, right? Because my base has an interval on one side, where on the other side you have a non-comprehensible. How is it going to be your example?
Yeah, the other side is no, yeah. Yeah, so non-compact.
So you want to.
Yeah. Yeah, because I want to deal with the action. Usually when you have a compact Calabi-Yau, then you do not have any action. Usually.
Okay, so here my L is the interval.
Your L will be this. This will be L.
That's the L.
Yeah, that's a Lagrangian fiber.
And you want to think of the line being the total space of all subguys.
Y check is the total space. Yeah. Yeah, exactly. Okay. Okay.
only with endpoints deleted.
Yeah, endpoints deleted, right? Endpoint deleted. Okay. Okay. Okay, yeah. Maybe. So let's say X tilde is a compact symplectic.
I see. So in that example, sorry, we delete the D in the 2 points which you deleted.
Yeah, the D is the 2 points.
Okay.
Yeah. I see. I see. I see. Yeah. Thank you for asking. Yeah. Okay. Then let me tell you the definition of 3D branes, and I will give examples. Okay. So suppose T is some torus acting on the X tilde with some complex movement. Okay. So so a definition. So a 3D brane on X, which is the y is hard. I see.
Also a question. When you say that assume L is T invariant, in that example, P1 example, is that automatically true, or that you have to?
I mean, yeah, the example, all the fibers are T invariant.
I mean, if you just to follow your definition of by check, is it true how the special Lagrangians are invariant?
It does not follow from this, but if you have one special Lagrangian which is T invariant, then the nearby special Lagrangian will automatically T invariant. Okay. I mean, yeah. So if you have one, then all the whole neighborhood is T invariant. So let me use the right. So 3D brane on X, which is X tilde quotient by T, which is the stack quotient by T's. Yeah. Is the data of a Kähler manifold Y, a PC invariant complex Lagrangian C tilde, which is contained in the pre-image of the Newman map of X tilde. And also you have a map
The family of 3D examples you had basically all fit into the diagram. Right?
yes.
Where you have wanted, you need to believe that if I take your very first example, so that is just like I guess this is just kind of like pure elongated.
Yeah, pure gauge.
That I can take my y to be y by check to be anything which projects to C and anything with C star. Anything.
Yeah, anything.
You draw that picture, it's a very nice.
Yeah, it's supposed to be anything, but for our XYZ transform, that has to be some condition. Yeah, I mean the family cannot be too strange. It more or less like.
Think of anything. I think about all of them.
Yeah, for those examples, I
Think of those examples that are being degenerated that makes sense. Much more rigid than like anything.
okay, yeah, I see.
Great.
Okay, and the Y, and also there is a Hamiltonian T action on Y. and then together with a T equivariant map to C tilde. T equivariant. Yeah. That looks complicated. Let me give you examples. Yeah, just for example 1. So when X is point quotient C star, so C star acting trivially. So if S1 acting on Y, which is acting on Y, which is Hamiltonian, okay, then we'll think of the Y. So we write Y symmetric quotient mapping to point quotient C star. Yeah. So this will be a 3D break. It's a 3D break of X. Okay. So in this example, the C tilde will be just a point. And you have an S1 equivariant mapping Y to point. Okay. So Y mapping to point is the S1 equivariant map. Obviously. Okay. So this is one of the examples. Yeah. And the other examples is an X is equal to T star C star. Okay. And with Y with any Kähler manifold, and you have a map to C star. Okay. This will, so we just write Y mapping to C star, and this is a 3D brains in T star C star. Okay, so these are two basic examples. Okay, so and for this example, the two examples are actually 3D mirror to each other. Okay. So you expect there is an SYC transform from a 3D brain on X in the example 1 to 3D brains for X in example 2. Let me write X rig here. Okay. So in fact, it is related to the Tellman conjecture. Yeah, I mean the part of the Tellman conjecture. It says that if you have some S1 action on a symplectic manifold, okay, then there exists a holomorphic map from Y check to C star. Holomorphic map. Holomorph. Okay. Okay. So far, so good. Yeah. And there is an SYC explanation. Okay. So you can write the pi check explicitly. So pi check is a map from Y check to C star, which is like R times S1. So you take a point here, which will be a Lagrangian together with a local system. And it is mapping to the moment map of L, and together with the holonomy or monodromy of the local system E at S1 orbit. If you want an example, it will like when you have a C star action acting on P1, then the 2D mirror will be C star with C and plus or minus 1, and the map will be just identity. This, yes, you can prove it. I would say not difficult. Okay, so I explaining when you have an SY action, when you have an S1 action on Y, then the SYC mirror will have a holomorphic map to C star. Okay, and now I'm saying that this map has an explicit formula using the moment map and holonomy. Yeah. Okay. I mean, that's a super potential for the mirror. Yeah. It doesn't matter. Yeah.
Why the other right map? I mean, I know that's the right map about your symmetry, but how do you explain how do you see that map that the same map as the map that Dalton talked about?
Yeah, I mean, for example, Hammond also said the following. It says that when you have the symplectic quotient, it should be 2D mirror to the pi check of some constant to the fiber of pi check. That's part of the Hammond conjecture. And actually, you can check these holes locally using this definition. You can check this to be true if you define both sides to be SYC mirror. That's something you can check. I mean, this.
Given why with the C star action, on the mirror side, there are at least 2 different maps with C star. Depending on the homologous non-quantum, that's some.
Yeah, I mean when you are taking the fiber, then you are like fixing the moment map and fixing the holonomy. So fixing the moment map is like you consider only the Lagrangian that's sitting inside the moment map level. That's why you corresponding to the symplectic quotient. Yeah. Okay. And there is a reverse direction.
I have to do T star S1 versus the T star. The
So here the C star is just parameterized by D.
Yeah.
And your Lagrangian is
I mean,
what?
Lagrangian these are the Lagrangian. Yeah, these are the Lagrangian.
And what does this have to do with?
And this is a moment map.
And the statement is that how is it related to the potential people economy? How do I discover there that the mirror is?
I mean, so far this is not related to the superpotential. Yeah. Yeah, there's an extra thing. Yeah, but one of the statements is that you can show that the pie chart is holomorphic using this definition.
What?
You can prove that this pie chart is holomorphic.
And what's pie chart in this example? You say it's D plus 100. D plus 100.
No, pie chart is the identity, sorry.
Oh, it's just the identity.
Yeah. Okay. Okay. Okay.
I think, I mean, so you think of like the absolute value of the zero to the 1.
Yes. Okay.
Well,
Okay. And for the reverse direction, when you have like C star n mapping to C star, with the map is given by the product, then you also, the 2D mirror for C star n is also C star n, and then you will have a C star action acting by diagonal action. Okay. If you want the XYZ explanation, that's a theta check. Okay. So for the XYZ explanation, we cannot explain that as a C star action, just an S1 action. Okay.
So.
Okay.
It's all about precisely Y and Y check being factored by Torah and all the consequences of that. So here, you're just picking a particular S1. I mean, so you wanted to say that this is a small piece of the XYZ where
Sure.
in my torus vibration, I pick a particular S1 and this goes. So in other words, you want to say the element protection is trivial.
Yeah, but I would say this is only part of the Teilman conjecture. Yeah. And also that is not the whole SYC. Yeah. So Teilman conjecture is not trivial. Okay. Okay. Yeah. So that is an SYC explanation for the other direction. So the S1 check, which is the set of U1 local system on the C star. Okay. So take a point here. Let me use LZ to be a local system on C star with monodromy equal to Z. Okay. Okay. So then the S1 action on Y check is just given by Z times L and E, sending to L and then E tensor with LZ. I mean, yeah. So we have a local system on the C star, and then you can pull back and then tensor with the local system on the Lagrangian. That will give you the S1 action. Yeah, and you can prove that this action is Hamiltonian. Yeah. If pi is holomorphic. I mean, you can write down explicitly the formula for the moment map. Okay. Maybe I'll use the other formula. Yeah, I mean, okay, another example, when X is T star C, and X rig will be T star C over C star. Okay. So 3D brain on X, maybe like a Taylor manifold Y together with a map to C, which is a complex Lagrangian in T star C. Okay. Yeah. And then our SYZ transform will give you a 3D brains in T star C quotient C star. Okay. And let me tell you the transform. Okay. So you have C, you have some Y here. Maybe I give you an example instead. So let's say Y is equal to C and you have a map to C, which is also product of Xi. And the idea is you first deleting the zero of C and then look at the P image. Okay. We call it YO. Okay. And then YO check is equal to C star N. And on the other hand, if you want to compactify your YO to Y, then you need to add some potential, which will be sum of Xi mapping to C. Yeah. And now YO has a holomorphic map to C star. So by the reverse direction of the Telemann map, by the reverse direction of the Telemann conjecture, you expect there is some C star action on the YO check. So there is some C star action. Okay. Yeah, and then one of our theorems says that this W.
You probably want to use different chords that we want to.
Maybe I put I here. Okay. Yeah. I mean, yeah, that Xi is C star equivariant. I mean, for this example, then you can just check that it is C star equivariant. But in general, you can use the SYZ picture to prove it. This map has to be equivariant. Okay, so you can quotient everything by C star.
The C star action being the shifting all axes together.
Yes, yes. Adding all the coordinates equally. So you can consider the same map, but you quotient everything by C star. Still the same map. Okay. And this will be a 3D brain in T star C quotient C star. Okay. Okay. This gives the mirror 3D brains. Okay. So far, so good. Yeah. Okay. So the general transform is similar. When you have some brain, some 3D brain, then you just delete all the devices and then look at the mirror and then compactify, you have some potential which will be equivariant.
So again, this statement of mirror symmetry is old.
Yes.
So
Okay. Let's write down the theorem. So suppose P sigma is a covariant variety with Tollway devices. X1 up to XL. And then Y is scalar. And then D is an anti-canonical divisor. So, okay, and then Y has a map to P sigma. Okay, such that D is equal to sum of the P image of the divisor together with some that does not relate to the Tollway divisor with D0, with phi of D0 does not contain in any HI. Okay.
Or like in the 3D brain matching, it has really respond. The zero section goes to zero section.
Yeah, it's from this conception, it's zero section go to zero section, but you may still have some superpotential. So you can use that superpotential to move it away from the zero section.
Yeah.
So may not be zero section.
So it's not the clean parallel.
Yeah, zero section go to zero section. But if you have superpotential, then you may use it to move it to fiber like that.
you're probably saying these operations of you must have that this operation of I delete something on one side in order to delete the origin of C.
Yeah.
That fits that itself fits into 3D mirror. But there's some 3D mirror meaning of it as well.
Yes, sure, sure.
And what are you saying? Intuitive is crucial, right? How you sort of want to solve, how you want to derive mirror symmetry.
Yes, yes.
Now you want to tell us probably that way of thinking about it has an actual explanation in 3D.
Yeah, because it is.
The diagram that you were drawing. Maybe you want to.
Yeah, because for this, I start with something that is the whole thing is a 3D ring in T star C. And then finally we'll have something in T star C mod C star. Yeah. So I mean that 2D mirror symmetry gives you the transform of 3D rings between these two 3D mirror pairs. Mm-hmm.
So if we were to draw this star diagram that you have for T star P1 for T star C is just a rectangle, and then you want to have me focus that so somewhere away from the origin of that guy, think about T star. Is that relevant?
You mean when T star P1?
Yeah. No, just T star. Your example of here, in this here, our x is just T star C, right?
Yeah, T star C.
And then to understand what mirror of y in T star C is, I want to delete the origin, turning T star C into T star C star.
Sure.
So I guess I have just your base.
Okay. Okay. Mhm. So there exists a holomorphic map for Y mapping to EL, which is holomorphic and T can equal what? Okay. Okay, so let me explain. So as before, so when we have a duality, just like before we have C, and then we have a 3D ring over that duality. And the idea to construct the 3D mirror ring is to first you delete all the devices that come from the toric devices. Okay, that's what I mean by YO. YO is Y, deleting all the devices that come from the toric part. And then William says that the 2D mirror of YO will have a map to CL, which is holomorphic and also has a teacher action. Okay. And the relation to 3D mirror symmetry is that we have not using just T star T and T star CL quotient by T check. These two are 3D mirror. Okay. Just remember the P sigma may be some T star N quotient by C star K. And so its 3D mirror will be T star N quotient by C star N minus K. Okay. 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 So it says that whenever you have a 3D ring here, support on a zero section, then you have an SYC type transform to give you a 3D ring on the 3D mirror. Yeah. And the transform is similar to the example that you delete all the devices that come from the toric devices, and then take the SYC mirror and calculate the superpotential. Then we provide you some map. Okay.
And, so sigma is a fan, I guess.
Yeah, sigma is a fan.
What dimension?
Like for this example, this N minus K. Yeah.
And what is TQ? Does the
This L.
L
That's N. Sorry, that's
divided by T check?
maybe I use L. And T is just C star K. Sorry, T is just C star L minus K. Okay. Okay. Any other questions?
Theorems Given this data.
Yeah, given this data. Yeah. We can define this map. Yeah, just for this example, for the CM mapping to C example, this map is just sum of xi. So in general, it's just counting some holomorphic disk. Okay.
Suppose my P sigma is a battle and Y is P sigma itself.
Yeah. Let me give you this example.
It's a little difficult to see. I both knew the 3D mirror symmetry and I knew the 2D mirror symmetry.
Sure.
I'm not sure what. Am I learning about 3D from 2D or 2D from 3D? Which
Okay.
way it's gone? And in particular,
It's like giving you a 3D brain transform using 2D. Okay, maybe I should. Okay, so you start with Y mapping to P sigma. This is a 3D brain in T star P sigma. Okay. And now you have a map F, so YO check mapping to CL.
what's special about the zero section? Could I presume that, sorry, not as it's an example of a 3D brain in the space, right?
Yeah,
I
example.
have more general 3D brains that, for example, project the tangent fiber, or these are special.
I mean, the tangent fiber are also special.
Or many other.
Yeah, that can be other. Yeah, I mean, and then this film says that this will be a mirror 3D brain in the 3D mirror. That give you a 3D brain transform. So that use the T equivariancy. So that you can quotient it by T. Okay. Yeah. Let me. Just another example when X is T star P1 and my 3D brain is P1 mapping to P1, which is the identity. Okay, so for this example. And then the method to calculate it is to reshape it to the C star. That means you delete the CO and infinity fibers. Okay, and then its 2D mirror will be C star. The 2D mirror for C star is C star, but if you want to compactify it to P1, then you have two holomorphic map. One is Z and the other is Z 1 over Z or Q over Z, depends on the symplectic form of P1. Okay. And there is a C star action. On C star, the standard one, there is also a C star action on C2, so that the weight of C2 is 1 and -1. Yeah, and then you see that this map is equivariant. So you can quotient everything by C star. So C star quotient C star, which is just a point mapping to C2. So it is just a point mapping to this space. Okay. Yeah, that's related to the example I gave at the beginning of the talk. So this is T star P1. Okay, so suppose I start with that zero section. Okay, which is this Y. This is Y. And then the 3D mirror T star P1 is still T star P1. And then this point will be just a point here. Yeah, but of course the precise location of the point depends on Q. Okay. So that's related to the example I discussed at the beginning. Okay. Okay.
So here, can you lead it to north to south pole?
Mm-hmm.
Then you have there you have a C star.
Sure.
And then what? Then you would say, okay, mirror C star is
C star.
like that.
So you compactify, so you add back the two functions.
Yes, you'll get the two functions coming from the discount on the left and the discount on the right.
Yes, exactly.
Okay, why do I now I'm supposed to also know that I should sum them up. How do I sum them up? Because well, my divisor had two components. Okay, so I'll sum them up.
Yeah, I'm not summing them up.
You actually should, right? Get the breakdown.
It depends on your purpose. I mean, if you just want the mirror of P1, then yeah.
All right.
Well, the C star is, this C2 is not the 3D mirror for T star P1. You need to quotient out C star, then you will obtain the 3D mirror. I mean,
Okay, but how I see. But okay, I see this guy, it goes the other way. You have the two guys that will give you the two coordinates and the C star action. The thing that the thing has will tell you that the charge is a 1 and -1.
yeah, I see. And the C star action, yeah.
That deriving the 3D space in which this guy is going to live. Okay.
Sure.
Okay.
And our film say that the discount is compatible with the action. Yeah, and the picture for this example is this.
Okay.
I'm confused. So you define your T0 to be the difference between T and the fullback of the HI. Do you use T0 anywhere?
I mean, for those example, we do not have T0. T0 is empty. In the theorem, yeah, I mean, you're right. In the theorem, then if there's D0, then the Y0 check will be equipped with another superpotential.
Again, what is the special role of the P1? Suppose I took a different path. Suppose I took Y to be the attached fiber. It's still a good brain. Are you telling me that you're saying that there's some choices of brain inside X that are going to allow me to discover what X is? I think I don't understand.
I mean, if you taking this,
there that will allow me to discover the whole mirror, or what?
I mean, if you're taking this ring, then the mirror ring will be like a point here.
But it,
even actually, I three at the beginning, and then there's no match between the 2D and the 3D ring that are just bigger.
Maybe I think the interpretation is something like, you know what X and X should cut, and suppose someone gives you a Lagrangian inside X and a Y that knows how to map into that Lagrangian. You also know how to like do SYZ mirror symmetry to that one to get one check, but you don't know how to map on that Y check to a Lagrangian X. That's the new result. I think that's the point that's there. It tells you that there exists a holomorphic empty check at the very end there. So
Yeah.
it tells you how to construct.
It tells you. how to
Okay, no,
couple.
that makes a lot of sense.
I think that's the future.
No, great, perfect, no, that makes a lot of sense, yeah. I think
Okay.
you had probably said it, I just didn't understand, sometimes.
Yeah. Yeah, but thank you for asking.
Go beyond chloride.
Yeah, we can do some non-abelian case, but the method is to first do the abelian case and then leave it to the non-abelian world. Yeah. Yeah, okay. Mhm. Okay, let me talk about the equivalent. Thank you. Scalar and equivalent. Scalar parameters. Yes. Equivalent parameters. Okay. So in this examples, you have these are P1. Again, you see some action. And okay, and for this example, the Kähler parameters is x2. Okay, and this is let me call dt, and this for the t strict. So the Kähler parameter is just x2. X2. Second cohomology. The second cohomology.
Oh, okay.
Yeah. It's X.
I thought you wanted to write down a moduli space and the up that is ideally suited as complex parameters, no? Okay.
No.
That would be out of tolerance.
Yeah, by Kähler parameter, just Kähler class.
You want to linearize things or what?
I mean the Kähler form. Yeah, that's linear.
Yeah, but honestly, mirror symmetry goes far beyond that and concerns the whole moduli spaces, right? Not only the linearized things.
I mean, that's the 3D.
Yeah, upper half plane is the moduli space. It's a Teichmüller space for the complex structures of the power. Yeah. But H2 is every cohomology which you write down is a linear space, so that's always only a linear approximation to actual moduli space.
Yeah, that is a whole family over X2. And the map is given by the previous map. A family of deformation over the X2. I mean, for this example, the X2 is just one dimension. You have the whole thing like, yeah, X, Y. I mean, you have the whole deformation over the X2. Let's see.
Yeah. Okay.
Yeah, the whole deformation given by the previous map.
Yeah. This thing is not canonical in a sense, right? I mean,
It's canonical.
What?
It's canonical. It's universal.
Yeah. Okay. But just it's after isomorphism at most.
Okay.
Right. Something draw the Kähler structure. Yeah. Wow.
Yeah.
Not think too much. Why are we typing over H2 of X and not over not looking at actual moduli space?
I mean, this is the actual moduli space. I mean, that's the 3D Kähler moduli space.
The only way it's ever interesting is like if sometimes you consider the exponentiated parameters and consider like large volume limits, so you might take a exponentiate this and take some more fragmentation for like the Kähler moduli. Usually it's just however many, it's just rank H2 many forces. This is you interpret this as kind of logarithm, the logarithms of the actual versus the exponential.
No, like it's just the Kähler moduli is just like period in the other form. Like it's like
okay, so you divided out the equivalence between like which equivalence relation did you divide out then?
At this point, nothing. I mean, like it's really just those are the coordinates. Sometimes you consider you might want to look at like limits of their infinite large.
Yeah, I mean that's the resolution of the nilpotent orbit in SL2, and then the deformation is given by other coherent orbits. Yeah, so we have a family of coherent orbit over C. So for this example. Yeah, okay. So what I mean by Kähler parameter exchange or equivalent parameter means, first of all, there is an isomorphism between the Kähler parameters on one side and the equivalent parameter on the other side. Okay. Am I claiming that this is compatible with our SYZ transform? Okay. Any questions?
So if I give you any point in the H2 of X, you can give me everywhere non-degenerate omega is a negative point. And okay. We don't, okay.
Yes.
Cool. And on the equivariant parameters in that case, what's the difference to complex, something like complex structures?
It's not complex structure. It's not complex structure. It's just equivalent parameter. It means that there's some action. Yeah, but how is it related to the complex structure? That's when you have a 3D rings, and then you can use this action to add on the 3D rings. And then that action will deform the complex structure of the 3D rings as a family. Okay. Yeah, you can stay in this way. So there is a ham of X. It is the Hamiltonian group of X, and there is a KX that is the Kähler cone of X. There is an action of these two acting on all the 3D rings on X. Okay, and where the ham, so ham X is just a group, so it act on X, it acting on the 3D ring by changing its map. Ham is Hamiltonian group. Is the optomorphism of X together that's fixing the complex symmetric form. Okay. Yeah, and connected, and a Hamiltonian midway subcell. And then have acting on the brain by changing the complex structure. And also the Kähler cone, the complexified Kähler cone, acting on the 3D rings on X by changing the symplectic structure. Okay. So these two actions induce infinitesimal actions. Of P and also X2 on brain. Yeah. And what I was saying is that these two actions swap with each other under the SIC transform of things. Two actions switch just under the SYZ type transform of things. Really break. Okay.
And times H2 of X should be thought of as a combined Kähler and complex moduli.
Yeah, or compares Kähler and equivariant.
This space,
Derive.
no, fine.
Fine.
Derive the.
Okay. Okay.
Non-mathematics.
Okay.
Find this space as an invariant of X.
The cohomology.
Oh.
I mean the cohomology. I see. Okay. So
We're both together. We're
P in. Yeah, I mean, so first of all, ham is an invariant, right? Ham is an invariant of X. And this is a maximal torus. Yeah. Does he answer your question?
a bit kind of, yeah, I'm thinking of course in the larger picture in terms of stability conditions and deformation space. Both are in a sense categorical invariants, but both cannot be found at the same time. That's one of the classical problems in, I think, algebraic geometry. Thanks.
Yeah, okay. Okay. Yeah. Okay, and our theorem says that when you have a Y mapping to P sigma, and then the Y O check, you have a map to CL. Which is T check equivariant. Okay. Yeah, it has some symmetric form. Okay. And suppose you have some two form in P star P sigma, which go to Cassie in the equivalent parameter of the 3D mirror. Okay. Then this is okay. This is 3D mirror brings by our SYC type, by our SYC transform. Okay. Then we can perturb this Y by changing the symplectic form by adding the pullback of that omega. And then using our SYC transform again, this will be mirror to the same thing. At this time, you change the f, sorry, that's f. You will change this f to be f times the exponential of minus cosine. Yeah. Okay. So you have a pair of mirror 3D rings. If you deform one side by changing the symplectic form, then then that corresponds to you deform the other side by changing the map according to the equivalent parameters. Okay. So if you want an example, then that is example. When the y and p sigma are both equal to the 0 section in T star P1, and then the 3D mirror ring will be a point in the cotangent fiber. And then the location of the point will depend on the symplectic structure of the P1. Okay. Is anything okay?
So I understand, so you're saying, if we change the symplectic form of T sigma,
Mm-hmm.
that will change its mirror brings some sort of position.
Yeah, change the position.
Yeah. Like, act by
The action.
yeah. Right.
Yes.
Also, why I change this, I think, I change the complex, which is the, how do I change the complex structure?
Yeah, there is a corresponding theorem. You switch both sides. Yeah, exactly the same. You change the left-hand side by changing the pi using the action of the torus. Then you will change the symplectic form of the other side. Okay. Yeah. So the reverse direction is just the same. Okay. Any other questions? Sure.
Side, the thing you're modifying by that's like a Kähler cone. It's not a full route. It's only in one direction, right?
Yeah. So I'm considering the infinitesimal action.
Oh, just infinitesimal.
Yeah, I mean the only problem is when you add a two form, it may not be symplectic. But as long as if you have some y so that you add a two form, it is still symplectic, then the theorem is still true. It does not matter whether it lies in the Kähler cone. Okay. Yeah, that's what I mean by the exchange of equivariant and Kähler parameter in 3D are induced by the exchange of compact and symplectic structure in 2D. Okay, I hope this is clear enough. Sure.
On the right hand side, on the right up there, the Y check from T check.
Mm-hmm.
What is the Kähler structure that?
I mean the Kähler structure of the symplectic quotient. Yeah, I did not talk about this part, but I mentioned that the teacher action on Y is Hamiltonian. So there is formula for the moment map explicitly. So if you change the left-hand side by changing the pi, then the formula for the moment map will change accordingly. Yeah. Yes, exactly. Yeah. Yeah, maybe. Let me talk about the order structure. For the structure, okay. So for the structure, we're discussing for the structure for T star pom mod C star or T star and T star C star. Okay. Okay, and there is okay. So there is a diagonal map mapping point mod C star to the product of two point mod C star. Okay, then this induce a Lagrangian correspondence from T star from mod C star times T star from mod C star. A Lagrangian correspondence to T star from mod C star. Okay. So I will tell you what precisely the Lagrangian correspondence done on the brain level. So suppose you have a 3D brain here. So it's C star acting on some Y1, and you have some C star acting on some Y2. And then you apply this product structure, you obtain C star acting on Y1 times Y2. Okay, that's the product structure done with just taking product of two space with C star action. Yeah, I mean, yeah, you can think so. Or in other way, if you are brave enough to do calculation in the stacky level, then this is just the pullback of the diagonal map. Okay. Yeah, of course, you can think it as a definition. It's okay.
Also, U1 times U1 gauge theory, that thing has an interface to U1 gauge theory of strict diagonal subgroup. And if you take a product boundary condition,
Yeah.
and the U1 times U1, and you restrict the diagonal subgroup. Diagonal subgroup after your product.
Exactly. So that's why there is a diagonal, the corresponding to the diagonal subgroup. Okay. On the other hand, you have multiplication map from. So this is multiplication map that induce the Lagrangian correspondence from T star C star times T star C star to T star C star. Okay. So what does this map tell you? So T star C star has a vibration to C. Okay, so the whole thing is T star C star. And each fiber is a C star. Okay, so each fiber is a group. Each fiber has a multiplication structure. And this Lagrangian correspondence corresponds exactly to the fiberwise multiplication. Yeah, of course, you can think it as a definition. So fiberwise multiplication will give you a Lagrangian correspondence here. Okay. Let me give you an example to tell you why these two Lagrangian correspondences should be mirror to each other. Okay. 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 So for example, let's say a Cn with a C star action. So its mirror brane will be Cn, C star n mapping to C star with the product of xi, and then there is a potential which is equal to sum of xi. And then you can apply the generating function. Okay. Basically, it means that you take the graph for the differential w. You will obtain h is equal to vn inside t star c star. Yeah, just okay. Just for example, when n equals to 1, then w is just x. So when n equal to 1, then dw is just equal to x times dx over x. Yeah, I mean, that's the c coordinate, and which is z dz over z. Okay. So when you have n equal to 2, then it becomes n squared. Okay. So okay, so if you apply the first Lagrangian correspondence, you will send C star acting on Cn1 and C star acting on Cn2. It will be mapping to C star acting Cn1 plus n2. That's the first Lagrangian correspondence. Okay. And on the other hand, in the mirror side, if you have h equal to z to power n1, and then you do a fiberwise multiplication with h equal to z equal to z to power n2. Okay, so remember this is h, and the fiber coordinate is z. So you fiberwise multiply each other, then you will becomes h equal to z to the power n1 plus n2. Just multiply each fiber. Okay. Yeah. Okay. Okay. Okay, so how is it related to Telemann's ruling? Related to Telemann's ruling. So let me just give you a simple example to remind you what is Telemann's ruling. So for example, we consider the Coulomb branch for C star acting on C with the standard action. It is equal to T star C, the C2. Okay. And the pure gauge Coulomb branch is equal to T star C star. Okay. And there are two maps from T star C star to C2. Okay. So the first is x equal to xy, and then z equal to x, and then the other map is x equal to xy, and then z equal to y inverse. Okay, so in the picture, so this is C2. So for the first map, the x coordinate has to be invertible. So the image of the first map is the whole thing, but deleting the y axis. And the image of the second map is the whole thing, but you deleting the x axis. Okay. So let me call it x1, c1, x2, z2, and then the change of coordinate is x1 equal to x2 equal to x1, and z2, okay, maybe the other way. X1 equals x2, and z1 equal to z2 times h2. Yeah, that's the going. Uh-huh.
Function can reach z equal to h to the nth power.
Oh. Z equal to x. Yeah. Thank you. You're right. It should be z. Okay. Thank you. Z equal to x to power n. Okay. So again, yeah. So z equal to x n1, z equals x n2. So the fiber multiplication is you fix x and then multiply the z. Yeah. So you get z equal to x to the power m. Yeah. To fix the x and then the z coordinate are just multiplication. Thank you. Yeah. Yeah. Okay. So, okay. So if we want to calculate so I'm now calculating the Coulomb branch for C star acting on C. But I will calculate the 2D mirror for C star acting on C. Okay. So is mirror brings will be C star with function Z, and it has a map to C star, which is also C. Just the same, but when n equals to 1. And then you take the generating function. Generating function, you will have the h is z equal to h. Okay. So the upshot is that, okay, so let me call it this side. The change of coordinate star is fiberwise multiplying this Lagrangian. Okay. So by fiberwise multiplying, I mean you fix the h, but in the fiber coordinate you multiply the z. Yeah, that's exactly the change of coordinate. The x, you does not change the x, but for the z you multiply it with h. Okay. Yeah. Maybe I should end by telling you the general statement. I mean. Okay. So in general, you have T acting on V, and then you have the TC, you have the full Lagrangian correspondence. C on TC, form function by TC. And then you have the mirror 3D, mirror Lagrangian correspondence. Okay. These are Lagrangian correspondence. It does not have to be a map. Okay.
And, so you said there are two maps, two bulk maps from T star, C star, to C2. And they go
Okay.
on which maps of variety? So we are FNB, you wanted to show us now how Tillman's Leung.
Yeah.
In other words, how to interpret the results as.
This is, I mean, this is a map from T star, C star to C2.
Yeah.
Yeah, exactly.
Yes.
Yeah, and this is change of coordinate for the two map.
Oh, okay, so, and, yeah. Sure. But why do we define these maps?
Yeah, I mean, these are canonical map. I mean, so if you think of C2 as T star C, then C star is an open subset of C. Okay, so that gives you one map. And for the other map, you think of T star C as T star C dual, then this gives you another map. And you will have to.
So you said you wanted to make the relation between elements to do it explicit.
I mean, that's the Telemann school. Right?
If you look at Constantine's paper, he'll like write formulas like this for like what he says is you can look at the Coulomb branch of gauge theory with some matter, and he'll try to say that you can obtain this by gluing together two pure gauge theory Coulomb, right? And
yeah,
it might be a little bit hard to recognize because of this, everything is like C2 and potential C star as well. Like you think of potential C star as the pure U1 gauge theory Coulomb branch, and you think of C2 as the U1 hypercoulomb branch. But then you want to glue C2 on two copies of potential C star. And you specialize Constantine's formulas to this case. Like that. He's saying that you can understand these formulas by
yeah.
Because in Telemann's paper, it was just kind of observed that you could do this. Like, you know, from BFN to working right down on full branch and then kind of play around with things are zero and not zero, so together.
Say the example is with C2. So that's a higher dimensional example of the P1 that being moved together or not. It doesn't relate to that.
Well, it's saying that C2 you view as C2 is potential to C, which is a particular Coulomb branch. Now that's the Coulomb branch of gauge theory with matter. Okay. A general phenomenon is Coulomb branch of gauge theory with matter can be glued from copies of the pure gauge theory Coulomb branch.
Mm-hmm. Yeah, and that's the GUE method. Yeah. Okay.
So the D is mirror to the
T atom on V, yeah, to C star atom on C. Yeah. Okay. So the result is fooling. Yeah. You need to fooling carefully. Two copies of T star T check where multiplying, we are fiberwise multiplying with the mirror brane to be acting on V, we obtain the BFN Coulomb branch. Yeah. Okay, then that's the field. And yeah, I think that's all for today. Okay.
The second speaker.
Yeah, thank you. Sure.
So you had a few theorems about when you could construct the analog intelligence map, like a holomorphic T-check equivariant map to like star or whatever. Right.
So sorry, say again.
So you had a few results where you could construct Tolman's map for the SYZ error.
Tolman's map. Oh, okay.
Map,
You are not
yeah,
meaning
sorry.
this. I see. I see.
The map from Tolman's.
Okay.
Or like the
Sure.
What's like the extent and the breadth of that result? Like, was that the most general result that you have on the board for giving gauge theories, or do you have like a even more general result?
Yeah, for the non-abelian result. Yes, we have the non-abelian. You're asking about the non-abelian case, right?
Yeah, like most general version.
Yeah, I mean, yeah, the result is like when you G acting on Y, there's some non-abelian group, you can restrict it to the compare to the maximal torus. Okay, and by looking at the maximal torus, you have a brane, and have a mirror brane in the abelian Coulomb branch. Okay. Yeah. And then this Coulomb branch will be invariant to the wild group. And there is a map from the non-abelian Coulomb branch mapping to this. And we have a theorem say that you can always lift this brane to the non-abelian Coulomb branch. Yeah, so there exists a unique in here, which is a complex Lagrangian in the smooth locus mapping to this.
And somehow I can construct, so if I give you a Y, I can construct a Y check that like maps to that CG tree. Or
Yeah.
is it just that you can construct it's like Lagrangian, you can construct the dual of Lagrangian.
Yeah, you may have a family.
So you don't have to like compute the merit without happening. Like
Yeah, sure.
Can you do that?
Yeah, I'm not sure, but yeah, but abelian case will be fine.
No, I really think it's trivial, none of it.
Yeah, abelian case trivial.
It's not possible, but it's not possible.
Yeah. Yeah, I have not figured out it